Until now, we have only discussed scenarios involving constant acceleration, where the acceleration of an object is assumed to remain constant. For example, if you throw a stone from the top of a hill or a cliff, we typically assume the acceleration is constant, with a value of g equals 9.8 meters per second squared. But is this actually realistic? As the stone falls, it collides with air molecules, which create resistance and slow it down. This phenomenon is known as air resistance. Because of air resistance, the actual acceleration is not 9.8 meters per second squared. It varies over time depending on how much air resistance the stone encounters. Now, let's consider another example. Suppose you accelerate your car at a constant rate, then drive at a constant velocity for a while, and finally apply the brakes to bring it to a stop. If we draw the velocity versus time graph for this motion, it might look like a smooth, idealized graph. But is this type of motion realistically possible? For instance, when you accelerate the car, will it immediately achieve a constant rate of acceleration? Or will it take some time to reach that constant acceleration? Similarly, when you try to maintain a constant velocity, will the car instantly achieve it? The answer is no. It's not possible. The car takes some time to transition to a constant velocity after you stop accelerating. Even when you apply the brakes to decelerate the car, will it stop with a perfectly constant deceleration? Again, no. At first, the deceleration varies due to various forces acting on the car. Throughout this entire motion, several forces, such as friction, air resistance, and internal forces in the engine, are constantly influencing the car. These forces make it practically impossible to achieve perfectly constant acceleration or velocity. While this type of motion might be theoretically possible, it doesn't occur in real-life situations. A realistic velocity versus time graph would look something like this, much different from the idealized version. While questions about constant acceleration can be solved using SUVAT equations, solving questions involving real-life situations with variable acceleration requires calculus, specifically differentiation and integration. To solve these, we need to go back to the basic definitions of velocity and acceleration, where velocity is the change in displacement with respect to time. Acceleration is the change in velocity with respect to time. In terms of calculus, v equals ds by det, thus velocity is the derivative of displacement with respect to time, and a equals dv by dt, meaning acceleration is the derivative of velocity with respect to time. This means that if you know displacement as a function of time, you can differentiate it to find velocity. Similarly, if you know velocity as a function of time, you can differentiate it to find acceleration. Let's walk through an example. Now, in this example, we are given displacement as a function of time. Displacement equals 5t cubed plus 4t squared plus 3t. We need to find the velocity and acceleration of the object at t equals 3 seconds. Since we are given displacement as a function of time and need to find velocity, we differentiate displacement with respect to time. To find the velocity, we differentiate the displacement function 5t cubed plus 4t squared plus 3t. The differentiation of each term is as follows. The derivative of 5t cubed is 15t squared. The derivative of 4t squared is 8t. The derivative of 3t is 3. So the velocity function is 15t squared plus 8t plus 3. Now, to find the velocity at t equals 3 seconds, we substitute t equals 3 into the velocity equation. We get 15 times 3 squared plus 8 times 3 plus 3. This gives us 15 times 9 plus 24 plus 3 equals 135 plus 24 plus 3 equals 162. So, the velocity at t equals 3 seconds is 162 meters per second. For the second part of the question, we need to find the acceleration. Since we already have velocity as a function of time, that is, 15t squared plus 8t plus 3, we know that acceleration is the derivative of velocity with respect to time. So, let's differentiate it. The derivative of 15t squared is 30t. The derivative of 8t is 8. The derivative of the constant 3 is 0. This gives us the acceleration function, that is, 30t plus 8. Now, to find the acceleration at t equals 3 seconds, we substitute t equals 3 into this equation. Acceleration equals 30 times 3 plus 8 equals 90 plus 8 equals 98. Therefore, the acceleration at t equals 3 seconds is 98 meters per second squared. In this example, we showed how, if you are given displacement as a function of time, you can differentiate it to find velocity. Similarly, if you have velocity as a function of time, you can differentiate it to find acceleration. Now, the reverse process is also possible. The reverse of differentiation is called integration. If you have acceleration as a function of time, you can integrate it to find velocity. If you have velocity as a function of time, you can integrate it to find displacement. However, when performing integration, you need to remember to always add a constant c after integrating. This constant represents an unknown value that must be determined from additional information provided in the question. For example, if you integrate acceleration to find velocity, the result will include a constant c. To find the value of this constant, you will typically be given specific conditions, such as the initial velocity or displacement, which you can use to solve for c. Let's solve another example to see how this works. In this example, we are given acceleration as a function of time equals 5t, and we are asked to find the velocity of the object at t equals 5 seconds. Additionally, we are told that the velocity of the object is 10 meters per second at t equals 2 seconds. To find the velocity, we need to integrate the acceleration function. Now, integration of 5t will give us 5t squared over 2, so the velocity as a function of time is 5t squared over 2, and we will add c to that. Now, to find the value of c, we will use the given condition that the velocity is 10 meters per second at t is equal to 2 seconds. So substituting t is equal to 2 and v is equal to 10 into the given equation will give us 10 is equal to 5t squared over 2 plus c. Simplifying this, we will get the value of c as 0, so the velocity function becomes 5t squared over 2, so we can find the velocity at t is equal to 5 seconds by substituting t is equal to 5 into this equation. So v5 becomes 5 times 5 square over 2. Simplifying this, we get v is equal to 62.5, so the velocity of the object at t is equal to 5 seconds is 62.5 meters per second. So, let's summarize what we learned in this video. In most real-life situations, acceleration is not constant. To solve motion-related problems in these scenarios, we need to use calculus, specifically differentiation and integration. If we are given displacement and need to find velocity, we can differentiate displacement with respect to time to get velocity. If we have velocity, we can differentiate it with respect to time to get acceleration. Similarly, when working in reverse, if we are given acceleration, we can integrate it with respect to time to get velocity. If we are given velocity, we can integrate it with respect to time to get displacement. In the next video, we will solve some complex questions related to variable acceleration or some past paper questions. Please be sure to watch out that video. Thank you for watching this video. If you learned something new today, please don't forget to like this video and subscribe to our channel Top Grade Tutor for more content like this. Thank you, and see you in the next one.